All right, welcome everyone. So in case you weren't aware, today is the day of our third midterm exam. This exam will be covering all of multiple integrations, so all the double integrals and all of the triple integrals that we've done. But the lecture on vector fields that we had last Friday, that will not be included on this exam. That will be on the final instead here. So what we're going to do today is we're just going to have an open review session. So I think Dr. Huang has already done reviews with the practice exam on Canvas and the fall of 2019 exam, I think it was. And I've already posted a video on the spring of 2018. So I guess if people don't have a lot of questions, I might just do the only exam that doesn't have a review posted on it, which is summer of 2016. But if people have a lot of specific questions, then I guess I will do those here. Actually, let's take a vote on that first. Who wants me to just do summer of 2016, and who wants me to do general questions? Remember, only vote once. Okay. Seems like summer of 2016 has a bit more support here. You should create a poll. Oh yeah, that's right. You could do that in this, can't you? Oh, this will be fun. Let's try this. Why is this showing up down here? What the heck? It's only showing like the window that has me create the poll is like below the screen. So I can't type anything into it and it won't let me move the window. Okay. All right, forget about the actual poll. I think I'll just do, I think I'll just start doing summer of 16 here. Although maybe I'll skip some questions that I think are easier so we can go over the ones that might be more helpful. So I think we're gonna do summer of 16. Okay. Let me get that up here real quick. All right. I'll work on the poll thing for the future though. That's a better idea than just randomly having people type in the chat. All right. So let's see. The first question here from summer of 16 has to do with what's called a density function. So the density function of a certain type of material is given by rho of x, y, and z is 1 over root x squared plus y squared. All right, so that's the density. What is the mass of the object with this density over the region? And then here's the region here. X, y, and z, such that x squared plus y squared is less than or equal to 1. So we're in the unit circle. And that 0 is less than or equal to z is less than or equal to root x squared plus y squared. So we're below a cone. We're supposed to find the mass of this object. Now, this isn't something we explicitly covered here, but they gave us a hint for this problem. So they pretty much told us how to do the problem. So the mass is going to be the triple integral over the domain of our density right here. So if we just integrate our density function over this region, then we will get the mass of this. All right, so let's go ahead and set this up. So let me ask you guys this: which coordinate system do you guys think would be most natural for doing this triple integral? Rectangular, cylindrical, or spherical? Cylindrical is right. That's right. We don't have explicitly a sphere in here, but we do have rotational symmetry, and we see a unit circle popping up. So that definitely says cylindrical. So let's put in our integrand. Now our integrand is 1 over the square root of x squared plus y squared. Another way of saying that is just 1 over r. And then we have r, because that's the Jacobian for cylindrical coordinates. And then we have dz, dr, d theta. All right, now let's see here. What are our bounds for z going to be right here? Well, let's see, z, lower bound of z is 0. And then the upper bound, if we write this in cylindrical coordinates, this will be r. All right, and then r, well, we're on the unit circle, so r will go from 0 to 1. And then they don't really say anything limiting us to the first octant or anything like that. So we're just going to go from 0 to 2 pi here. We're going to go all the way around this cone right here. All right, so then let's go ahead and do this integral here. And conveniently, the integrand is even simpler than it once was. And we just have 1. We're doing the integral of 1 dz dr d theta. So I'm going to do the integral of 1 with respect to z. And we end up getting r. So we plug in r for z, then we plug in 0 for z, and then we just get this. And then this is an integral that we can split up right here into 0 to 2 pi d theta, and then 0 to 1 r dr. So the integral from 0 to 2 pi of just d theta will be 2 pi. And the integral from 0 to 1 of r squared, I spoiled it, will be r squared over 2 from 0 to 1. So what do we end up here with? Well, we plug 1 and 0 in here, and we get a half. And so we just end up with pi in general right here. So pi is going to be the mass of this object right here. All right. And even though we didn't go over the specific formula in class, this definitely would be a fair question because they gave you a hint that told you how to do the problem. So something like this could actually be on there. All right. So let's see. Let's go to the next one here. The next one just asks us to compute an integral. So what do we have to do? We have to compute the integral from 0 to 1 and the integral from 2 to 3 of 1 over x plus 4y cubed dx dy. Yeah, what's up?
If you have a question for an integral that involves spheres and cylinders,
So the question was, if we had an integral that has both spheres and cylinders, would we still use cylindrical? It really depends on how they set it up, but most of the time I would say yes. I usually default to cylindrical unless there's a good reason to use spherical. All right, so let's see here. Let's go ahead and do this integral. And I don't think it'd be too hard to do it in the order that it's given right here. Because if we integrate with respect to x here, we have 1 over x plus a constant cubed. Well, integrating x plus a constant to a power is the same as just integrating x to a power. So what is going to happen with this? This is we're going to raise this power to be -2, and then we'll divide by -2. So we end up with this as our first result from the first integral right here. All right, and then I'm going to go ahead and plug in 3 for x and then 2 for x here. So I have my integral from 0 to 1 of -1 over 2 times 3 plus 4y squared. And then I'm going to put a plus because I'm subtracting a negative. And then I have 1 over 2 times 2 plus 4y squared here. All right. So let's see here. Now we need to do this integral right here. And technically what we would do here, I'm not going to really write this out, but I'm just going to explain what's happening here. We're going to do a little u substitution where u will be either 2 or 3 plus 4y, depending on which one we're doing. And du will be 4 dy. So we would just divide by 4. So I'm going to do the same thing that I did for the previous integral, only this time I'm going to divide by 4 because I have a coefficient of 4 right here. All right, so what do we get for this now? Let's see. We have the integral from 0 to 1, and then we have 1 over 8, because we're dividing by a 4, and then we have 3 plus 4y. Now, where did the negative go? Well, I raised this to be the negative first power right here, and then I divided by that -1 right here. Uh-oh, the sound's messing up again. Okay. Okay, hopefully that fixed it. All right, so we have this for this integral. And for the next one, for the same reason, we're going to have 1/8 and then 2 plus 4y here. Oh, we already did the integral. Whoops, we don't have that anymore. And this goes from 0 to 1 right here. All right, let's plug in our number and see what this ends up being. So I have 1 that's plugged into here. So I have 1/8 times 7 is 1/56. I subtract, and I have 8 times 6 minus 1/48 right here. And then I subtract and plug in 0. So I have minus, and then I have 1/8 times 3, which is 1/24. And then I have plus 1/8 times 2, which is 1/16. Ooh, this is kind of icky right here. All right. Well, anyways, this is what we get here. Looking at the multiple choice answers, though, this doesn't look like any of them in an obvious way. Let's see here. Well, we did the important part. We did the double integral here. So I think I'm just going to leave it at that. Unless, I don't know, did I make some kind of mistake here? I don't think I did. Everything seems okay. All right.
When you like what I did was simplify the first 3 fractions because it was like or the last 3 fractions because it was like 2, 3, and 6, and I think they canceled out, so it was like 1/56.
Oh, right, because this is 3/48, and this is 2/48, and 1/48. Oh, yeah, so all these cancel out. Yeah, thank you for the observation. All right. Oh, sorry. Okay, there we go. It's 1/56. Yeah, thank you for that observation. I was about to grind into it and like try to find a common denominator. That'd be terrible. All right. Let's see here. All right, find the volume under the function. So here's our function, f of x, y is x squared plus y squared over the region between the circles x squared plus y squared equals 1 and x squared plus y squared equals 4 on the xy plane. Okay, so we're finding the volume underneath a surface here. So what we could do is we could do a double integral of this over the area that we're looking between. Now, let's see here. We're having a double integral over the region between 2 circles. So that suggests to me that we should maybe turn things into polar coordinates. So that's exactly what I'm going to do here. So I'm going to turn this into polar. Okay, let's see. So x squared plus y squared in polar will become r squared. And then dA will be an r dr d theta right here. All right, so let's see. Now, what are our bounds for r? Well, we can only go in as far as this smaller circle, which has radius 1, but we can go as far out as this larger circle, which has radius 2. And then finally, they don't give any restrictions on, being in the first quadrant or anything like that. We can go all the way around the circles. So this says that we should go from 0 to 2 pi here. All right, so let's see. So this is r cubed. And then since this we could split up over multiplication, I'm going to write it like 0 to 2 pi d theta and 1 to 2 r cubed dr. All right, usually this happens with theta. Poor theta doesn't get any action at all. It's always just going to end up being 2 pi. And then we have this. And then this will be r to the 4th over 4 from 1 to 2. So let's see, this is 16/4 minus 1/4 right here. So that's 15 over 4 times this will give us 15 pi over 2. So that's going to be the volume underneath this surface. which is actually going to be a paraboloid, because this is z is x squared plus y squared right here. All right. Good, we got that one. Chugging along here. All right, number 4. Number 4 asks us to evaluate the integral of f of x, y, z is 2y over the solid bounded by the paraboloids. Z is 8 minus x squared minus y squared, and z is x squared plus y squared. All right, let's see here. I already see some people in the chat saying we should do cylindrical, and that sounds like a pretty good idea to me. So let's draw a picture of this real quick, just so we make sure what's going on here. Z equals x squared plus y squared is our bottom bound. So that's going to be a paraboloid looking like this right here. So there's our bottom paraboloid, x squared plus y squared. And then our top paraboloid starts at z equals 8, so like maybe somewhere up here, and then it decreases. So it's going to come meet this paraboloid down here. And their area of intersection, or the region of intersection, will end up being this circle, which is centered at the origin. And that circle right here is going to be our region of polar coordinates. All right, so let's figure out what kind of circle that is. So the region where they intersect is where we set these equal to each other. We have x squared plus y squared is 8 minus x squared minus y squared. I'm going to add these over here. I'm going to divide by 2. And then we see that x squared plus y squared equals 4 right here. So this is going to correspond to r equals 2 in cylindrical coordinates. All right, so let's see here. Let's write our triple integral here. Our integrand, we're not finding a volume, so our integrand is going to be 2y here. We get an r. Oh, wait a minute, we're doing cylindrical, so I can't write y. What would I write instead of y for this? It's going to be r sine of theta, right? I was thinking it'd be weird to have an ry here. And then we were going to put r dz dr d theta. I think I saw a question in the chat asking, how do we know that we're supposed to set these equations equal to each other? So from the picture here, we can see that these are going to meet in some kind of circle when they cross each other. And we're trying to find the solid that's bounded between the two of these. Now, what we're doing is once we do the z integral, which will go from z is r squared to 8 minus r squared, we need to figure out what's going on in the r theta or xy plane. And the region where these guys intersect is as far out as we're going to go in the r theta plane. So that's going to help us figure out what our r and theta bounds are going to be here. So that's why we set these equal to each other, to know how far we go out in the xy direction or the r theta direction. So yeah, and using this knowledge now, we know that we go from all the way from here into the origin, all the way out to 2. So our r shall go from 0 to 2. And once again, theta will go from 0 to 2 pi, because they didn't say anything about the first quadrant or anything like that. All right. Let's see. So let's go ahead and do this right here. They do ask us to evaluate this one. By the way, I'll give you a little sneak peek of the exam here. A lot of the questions on the exam will actually just have you set up the integral, because even if you know exactly what you're doing, grinding through a bunch of these triple integrals is time consuming, even if you immediately know how to set them up, which is not always the case. So a lot of the questions on the exam are just going to be setting up integrals, and then you don't actually have to do them. But a few of them will ask you to do it. So this one will be kind of like one of those. So we have 2r squared sine of theta. So let's do the z integral of this. Okay, so we have 2r squared sine of theta, and we're just going to tack a z onto this, and then we're going to do this minus this right here. So we're going to end up with 8 minus 2r squared. if we kind of blow through this part right here. Because we would stick a z here, and then we do this minus this. All right, and then now we have a multiplicative or a function we could split up over multiplication. This time theta actually does get some non-trivial contribution. We're going to go from 0 to 2 pi right here. And then we're going to have 0 to 2, and then we're going to have, what is this going to be? 16r squared minus 4r to the fourth. Okay. Let's see here. Oh, this is this is gonna be a little bit goofy. So does anyone know what this integral is gonna be here? That's right, it's gonna be. Yeah, this integral is just going to be 0 because yeah, the integral from 0 to 2 pi of sine, because sine looks like this, you have an equal positive area to negative area. So you're just gonna get 0. So all of this setup, and we end up just getting 0 right here. Now, it might be kind of surprising, like, oh, wait a minute, we're doing something between two paraboloids. How could we possibly get 0 for that? Remember that they're not asking for a volume for this one. They're actually asking for the triple integral over 2y right here. So this doesn't represent a volume at all. This represents something else, but not volume. So it's okay to get 0. Now, let's see. I think I saw a question here. When do you know to do a triple integral or double when it asks for volume? You could do it either way. So you could do the double integral with the top surface minus the lower surface, or you could do the triple integral of 1. They end up being the same thing, provided you set up your integrals correctly. So you could do it either way. All right, let's move on to the next one here. Okay, so this one's talking about something called parabolic cylindrical coordinates. Well, let's see what that is. All right. So parabolic cylindrical coordinates send x, y, and z to u, v, and w. So I smell a Jacobian coming. By the transformation given by p of u, v, w is, oh wait, no, sorry, the last coordinate was a z. So then we have, what do we have? uv, u squared minus v squared over 2, and z. So I guess we could kind of see why they would call this cylindrical, because we're keeping our z exactly the same, just like we do with cylindrical coordinates. Okay, now what are we supposed to do here? Compute the absolute value of the Jacobian. So we don't need to do an integral with this or anything. We just need to compute the absolute value of the Jacobian. All right, well, let's set up our Jacobian here. So we have x is uv, y is u squared minus v squared over 2, and z is z right here. All right, so let's see. My u derivative of x will be v. My v derivative of x will be u. And my z derivative of x will be 0. There aren't any z's in there. All right, next, my u derivative of y will be, let's see, I bring the 2 down, so it's going to be u. My v derivative of y will be negative v right here. And my z derivative of y is, well, 0. Okay, then z is very simple. There are no u's in here. There are no v's. And z equals z. So the derivative there will just be 1. All right. So there we go. Yeah, z is z. Yeah, hard to go wrong with that one. All right, so let's go ahead and do the determinant of this. So let's see. So we have v times negative v 0, 0, 1. Then we have negative u and u 0, 0, 1. And then the last minor would have a coefficient of 0 times this matrix, but it's just going to be 0. So what do we get here? Let's see, we have negative v squared minus u squared. So this is negative u squared plus v squared. All right, so that is the Jacobian but the absolute value of the Jacobian will just be u squared plus v squared right here. So we put on the absolute values here. All right, so there we go. There's the absolute value of our Jacobian if we did need to do an integral with this coordinate system. All right, number 6. Integrate f of x, y is x over the region bounded by y is x squared and y is x plus 2. And then the region, y is x squared, y is x plus 2 right here. All right. Let's draw this. Y equals x squared, looks like this. And y equals x plus 2 looks like this. So we're going to be integrating over this kind of crescent looking region right here. All right. Let's go ahead and set up our integral here. So our integrand is x. And I think it'd be a bit more natural to do this with respect to y first, since we have our upper and lower y bounds. And then we can follow that up with x right here. All right, so our lower bound for y here is going to be x squared. That's the lower function in terms of y. And then our upper bound will be x plus 2. All right, now we need to see where these guys intersect so we know what x values to have. So we have x squared is x plus 2. Let's see, so that's x squared minus x minus 2 is 0. And if we factor, we end up getting this right here. So x is -1 to 2. So those will be our bounds. So this presumably is -1, and then this will be 2 right here. All right, so then this one isn't too bad to do. The integral of x with respect to y is xy. That's from x plus 2 to x squared. All right, and then we go ahead and do this. So we have x times x plus 2 minus x cubed. And this can be written as x squared plus 2x right here. And then finally, we do this part. So we have x cubed over 3 plus x squared minus x to the 4th over 4 from -1 to 2. Okay, unfortunately, we don't have 0 as a bottom bound. It makes polynomials twice as annoying. So we put 2 in here. We have 8/3 plus 4 minus 4. Okay, so those cancel. And then we subtract, we're going to subtract -1/3, so that's plus 1/3. We're going to subtract -1. No, sorry, we're just subtracting 1. And then we're going to subtract -1/4. Okay, so there we go. So this combined is 3, and then we have 2, and then plus 1/4 is 9/4. So that ends up being our result for this. All right. Yeah, see, this is what I mean. We spent like maybe half the time setting it up, but then like, even though this was an easy integral to do, you end up kind of burning a lot of time on it. All right, let's take a look at this next one. This looks interesting. Okay, the next problem. Evaluate the integral. All right, it's a triple integral over some domain, and it's e to the x squared plus y squared plus z squared, all raised to the 3/2. Okay. And D is the region above the cone. Z is the square root of x squared plus y squared. And below the hemisphere, Z is √1 minus x squared minus y squared right here. Okay. So let's see here. So we have a cone and a sphere, so there's definitely some kind of circular symmetry here. Are we going to keep sticking with cylindrical coordinates, or are we going to switch over to spherical for this one? All right, we have one spherical, one cylindrical, we have sphericals. Yeah, this one we're actually going to end up using spherical. And reason for that is that, well, we have a sphere in here. That's one point in spherical coordinates favor. I'm mostly looking at this integrand though. We have x squared plus y squared plus z squared. That we could just all simplify down to just be a rho squared. Whereas even if we use cylindrical here, we would still have r squared plus z squared, and that's still going to be awkward raised to the 3/2. It might be doable. I don't know about that. I actually don't think it's doable if we do it that way. So we're going to have to use spherical for this one. All right. So let's go ahead and change everything to spherical. So we have our triple integral. And just as I just said, this is going to be rho squared right here. So this is rho squared. And then that's to the 3/2. So this will be e to the rho cubed. Then since we're doing spherical coordinates, we have to put our Jacobian in here, which is rho squared sine of phi. D rho, d phi, d theta here. Could I draw what the bounds are going to look like? Yeah, so this one's going to be one of those ice cream cone looking ones. So we have our cone going out like this. So here's our cone. And then it's bounded above by a sphere right here. We end up having something like this. So this is the region that we're integrating over. We're not just finding its volume, we're actually integrating this function over that region here. So that's what this is going to look like right here. All right, so let's see here. Let's try to set up the bounds here. So whenever we include the origin, we should probably do rho equals 0 as our lower bound, because we need to get all the way back to the origin, which has coordinates rho is 0. Now let's see, so we can extend outwards in the rho direction as far as rho equals 1, which is this hemisphere right here. So our rho will simply go from 0 to 1, because we have as our outer bound this sphere of radius 1 right here. All right. Let's see here. Oh, this is the one you were talking about with x equaling 0. Yeah, so that makes the 5 bounds really easy. That's right. Yeah, so let's take a look at that. So one thing we can do if you have circular symmetry around the z-axis is you could simply look at it in the yz plane like this. So here's kind of the top of our sphere, and then here's the cone right there. And then this is our angle phi. So we notice that phi is going to rotate downwards all the way starting from 0, because that's the upper axis here. And it's going to rotate down all the way to this cone. Now, does anyone remember what phi, the cone z, is root x squared plus y squared is? That's right. It's going to be pi over 4. And what if we didn't know that? How did we get pi over 4 from this? Well, z is equal to r right here. All right. And then let's see. I always mess up which arc function this is. So we have z and r. So phi is going to be arctangent of r over z. And since they're the same, this will be arctangent of 1, which is pi over 4. Why is it not pi over 4 to pi over 2? Because starting up here on the z-axis, this is phi equals 0. So phi starts at 0 right here, and then it opens up downwards like this. So we're starting at 0, and then we're rotating down to this angle, which is going to be pi over 4 right here. Why is rho going to 1? Because we're going outwards to a sphere of radius 1 from the origin right here. Okay, so we have our phi bounds, and yes, so courtesy of Michael here, this is actually a good way of kind of visualizing this. If you have symmetry around the z-axis, you can kind of flatten it and view it like this if you'd like. All right, and then since we are going all the way around the z-axis, our theta will be from 0 to 2 pi right here. All right, so we're supposed to evaluate this integral. So let's go ahead and do that. Let's see here. Now, this integral previously wasn't doable in Cartesian coordinates, but now it's pretty easily doable now, because all we need to do is a u substitution with u is rho cubed. So if u is rho cubed, du will be 3 rho squared d rho. But we don't have a 3 lying in there, so we'll just divide by that. All right, so now our integral is 0 to 2 pi, 0 to pi over 4, 1/3 e to the u sine of phi. Oh, whoops, I forgot the integral for u. Then we have du, d phi, d theta right here. All right, and actually the bounds will be the same for this integral right here. Because we have 0 goes into here and gives us 0, and then 1 goes into here and gives us 1. Isn't phi arc cosine of z over p? Yeah, it is, but it's also equal to arc tangent of r over z. So those formulas are both valid, whichever one ends up being more useful here. Let's see. All right, so now we can actually do the multiplication rule here because we actually have all 3 of our bounds are constants here, and we could split up our function over multiplication. So we have 0 to 2 pi d theta. We know what's going to happen with that. We have 0 to pi over 4 of sine of phi. Okay, so this will be a little more interesting than the sine integral we had before. And then we have 0 to 1 of 1/3 e to the u du right here. Okay, this is going to give us 2 pi. The integral of sine is negative cosine from 0 to pi over 4. And then the integral of this will be 1/3 e to the u from 0 to 1. All right, let's see here. How is this all going to pan out? So we have 2 pi over 3. We move that constant out. And then we're going to have 1 minus root 2 over 2 for this part. And then we're going to have e minus 1 right here. So let's see. Oh, this doesn't quite match some of the multiple choice answers. I think they moved the 2 in there for these. So we have 2 minus root 2 times e minus 1 times pi over 3. That is one of the answers here. So there we go. All right. Let's see. Got that one. That's good. That was a good problem with spherical. What we got next? View the area of the region bounded by the lines y is 0, y is 2, y is 2x, and y is 2x minus 4. That's just doing a double integral. I think I'll maybe skip that one. I'll come back to it if we have time, but I think that one's pretty easy. Number 9 is actually one that we were instructed to skip. This is just talking about mapping things between r, x, y, and z and rho, phi, and theta. Don't really worry about that problem. Number 10, this is something that we want to do right here. All of the exam recordings can be found either on our front page of Canvas, or if you click on exam, I think it's resources or something like that. You can find all that information there. All right, so all we need to do here is evaluate this double integral. There's a little bit more to it than that. Okay, so what would be the problem if we tried to do the double integral just as it's written? Well, that would require us to do the integral of e to the y cubed, and I have no idea how to do the integral of e to the y cubed. So I think I'm going to have to change the order here in order for us to have any hope of doing this. All right, so in order to change the order of integration, let's go ahead and figure out what our region looks like. So our region is bounded from y equals x to y equals 1. So that's from here to here. And it seems like x goes from 0 to 1 right here. All right. So this is the region that we're integrating over. So now I want to convert this into an integral that begins by integrating x and then integrates y. So let's see here. Our leftmost x bound is x equals 0. And our rightmost x bound is this right here, x equals y. So our new integral will go from 0 to y right here. And then y ranges from values going from 0 to 1. So this will be the new order of our integration here. Use Wolfram Alpha and Symbolab. They could give you numerical approximations. They can't give you a nice function for your antiderivative. All right, so let's go ahead and integrate this with respect to x. So this becomes x squared e to the y cubed from 0 to y. And then I put y in here, and I have y squared e to the y cubed. All right, and then now this integral is much more doable because we could just do a u substitution. We could do u is y cubed, and then du over 3 will be y squared dy right here. Oh, isn't it x squared over 2? You're right, it is x squared over 2, my mistake. Okay, so we have over 2 here, and then we're going to end up with 1/6 the integral from 0 to 1 of e to the u du right here. All right. So let's see here. Why did I just keep the bounds as they were? Because like the previous problem, if I put 0 in here, I have 0 for u. If I put 1 in here, I just get 1 for u. So these are going to be the same. So this ends up giving me 1/6 e to the u from 0 to 1. Another way of saying that is e minus 1 right here. So we have 1/6 times e minus 1 as the result of this integral. So sometimes it's necessary to change the order of integration here, and that's how we do it. All right, number 11 actually talks about something that was on the previous exam, so we're not going to talk about that. It wants us to find extreme values with Lagrange multipliers, but we've already done that. All right, number 12, set up the integral, the triple integral of x z dv, where w, well, let me just write it out. I'll waste more time just saying it verbally. So we have the triple integral of x z dv. Okay, and this is over the region w, where w is the region bounded by the elliptic cylinder. And what's the elliptic cylinder? It's x squared over 4 plus y squared over 9. And the sphere, x squared plus y squared plus z squared is 16 right here. All right. So let's see here. We need to set up this integral, and all of the multiple choice answers give us our integrals in rectangular coordinates. So it's it's good news that we just need to set this up, because doing this integral in rectangular coordinates would not be pleasant. Furthermore, all of the orders of integration go dz, dy, dx. Okay. So let's see. So we're within the cylinder here, and we're also within the sphere. Oh, it says in the first octant as well. I always seem to miss that when it says that. In the first octant. That makes things a bit easier. So if we were to draw this, what we would get, so we have the elliptic cylinder, which will look like this, and then we have a sphere of radius 4. So we end up with kind of an area or a volume that looks like this right here. So our lower bound for z in terms of surfaces right here is 0, because we're bounded below by the xy plane down here. And then we are bounded above by the sphere. Now, in terms of z, this is going to be the square root of 16 minus x squared minus y squared. That's the equation of our sphere in terms of x and y. Okay, so we've done that. Now let's pay attention to what the y bounds are going to be. So we kind of squash everything down to z equals 0, and we're just focusing on this region right here. All right, so this region is bounded by that elliptic cylinder, right? So what we're going to do is we're going to solve for y here, because now we're doing things with y equals stuff. So y squared over 9 is 1 minus x squared over 4. Y squared is 9 minus 9/4 x squared. And y will be the square root of 9 minus 9/4 x squared. Okay, but none of these show up as an answer choice. Let's see here. So it appears that whoever wrote this exam factored out a 9. And then they also factored out a 1/4. All right, so it seems like we end up with this as our upper bound here. So we have 3/2 square root of 4 minus x squared. And then since we're in the first octet again, we have y equals 0 as our lower bound here. And then finally for x, we just see which two numbers x goes in between. What are those two numbers? What is x going to go in between here? All right, that's right. It's going to be from 0 to 2. Absolutely. So there we go. We've been able to set up this integral. Now, doing this integral will be another story. Actually, I don't think this one would be too bad, because we would get this and make it be a z squared, so we would square that. So actually, this one wouldn't be too bad to actually integrate. But if we didn't have that z there, it might be different. All right. We got that. Why not 0 to 4? Because if x went all the way to 4, for example, then here we go. If x all the way went all the way to 4, we would have 4 squared over 4, which would be 4, and then plus some positive number. There's no way that could equal 1. So each of these terms individually can only be as big as 1. So even if y is 0 here, x can be at most 2, because we need to square this and divide by 4, and it needs to be 1.
Why don't you use the other equation, like the sphere equation?
Oh, I did use the sphere for the first bound right here. The sphere is our upper bound for z right here. All right. Let's see. What's 13? We having time for 13? Oh, yeah, we do. Okay. The point r, theta, and z in cylindrical coordinates can be converted to spherical coordinates as, okay, so let's see. So we have r, theta, and z is going to be 2 pi over 4 and -2. All right, and then we want to change this over to rho, theta, and phi. All right, so what is this going to look like in spherical coordinates? Well, first of all, we have literally the same coordinate here in both of these, which is theta. So we're definitely going to have theta as pi over 4 for this, no matter what. So that can kind of that can help us eliminate some of these answer choices, because believe it or not, they have some that aren't pi over 4 for theta. All right, now for the rest of these, let's see what we got here. For phi here, remember from the earlier problem that phi is going to be arctan of r over z right here. So let's see, our arctangent of r over z ends up being -1. So ordinarily for arctangent, this would be negative pi over 4, but we only want angles in between 0 and pi right here. So what angle is this going to end up giving us? It's not negative pi over 4 like arctan normally is. What is it going to be here? That's right, it's going to be 3 pi over 4. Like that. We're going to have phi is 3 pi over 4. Oh, that already eliminates all of the other answer choices and only narrows it down to 1. But in case it didn't, how would we get what rho is going to be? Well, it turns out that rho squared is x squared plus y squared plus z squared, right? But another way of saying this is rho squared is r squared plus z squared. So for this problem, we're going to have rho squared is 4 plus 4, meaning that rho is the square root of 8 or 2 root 2. So that will be our final coordinate right here. Let's see. Yeah, tangent of phi is r over p is probably the better equation, now that you mention it. This is probably the better way of imagining it. And we need to remember that phi is always in between 0 and pi. So these two facts right here can help us get those. Could you also use r is rho sine of phi? Yeah, that's right. Yeah, once you know what phi is, then yes, you could do it that way as well. There's a lot of different ways of doing this one. However, one way I would suggest not doing it, and I know this may have been tempting for some people, is don't turn this into Cartesian and then turn the Cartesian into spherical. That's definitely going to take longer than it needs to. So I recommend maybe not doing it that way. But yeah, besides that, there are many different ways of doing this right here. All right. Let's see what we got next. We have enough time for another
Professor
one?
Manley,
Yeah, what's up?
for 13, wouldn't you make it 2 root 2, 3 pi over 4, and then pi over 4? Because theta on the question is the last coordinate rather than the second one.
Oh, you're right. You're right. Oh, I totally missed that. Yeah. Yeah, thank you. So the question wrote it like this. But thankfully that also appears as an answer choice. Yeah, thanks for catching that. See, even if I write an exam or something, I would just get a 95 on it because I would do something like this, and then I would totally mess it up. All right. All right. So because of that, let's see. Oh, do we have enough time for another one now? Find the area of the shaded region using polar coordinates. We'll at least set up the integral, and then I'll leave you guys to do it. All right. So we have this right here. And then we have this coming out like that. And then coming in here. Okay, and we want to find this area right here. Okay, and then this curve is r is 1 plus cosine of theta. And this is r is 1 right here. Okay, so in order to find the region between two different polar curves, we could just do the double integral of r dr d theta, like that. So where our r bounds, we have 1 plus cosine of theta is going to be our outer bound. And then it seems like r equals 1 is closer to the origin, so that will be our inner bound right here. All right, and then let's see, we need to know what our theta is. So I think it's pretty clear that we start at theta equals 0 right here. And then we keep rotating around until we get to this theta where they intersect. So we have 1 plus cosine of theta equals 1. So this is where cosine of theta is 0, and that will occur at pi over 2. So our upper bound for this double integral would end up being pi over 2 right here. All right, so there we go. So that'll be our double integral here, and then I would leave it to you guys to actually do this one. This one we need to use a double angle or a half angle identity because of you would get a cosine squared there. So doing this integral would actually be marginally harder than most of them usually are. All right. So anyways, we're out of time here. Oh yeah, what's up? Yeah, so so if you want to avoid Calc 3 here, you could also do this using Calc 2 because it's multiple choice and we're not going to show you. So yeah, you could have just done the integral from 0 to pi over 2 of r squared over 2 d theta. All right, guys, that's it for now. So best of luck on the exam this evening. I hope you guys do well.